That delightful sound was the sound of the piezoelectric buzzer generating a 2 kHz frequency driven by the UNPACKED 555 timer. So the 555 timer consists of 3 main parts as shown in the UNPACKED 555. The op amp, the NOR SR latch, and the inverter. Let's take a dive into each one of these. So first, let's take a look at this chip, the LM358, which is a dual op amp chip. These op amps act as comparators. Here is a comparator. It consists of a non-inverting input, an inverting input, and an output. A comparator, as the name suggests, compares voltages. If the voltage presented on the non-inverting input is greater than the voltage on the inverting input, its output will be high. Otherwise, it will be low. In the 5.5 timer, there are 2 op amps. Additionally, there are 3 5K resistors, making use of the voltage division property of resistors, creating nodes with 2/3 reference voltage and 1/3 reference voltage. The node of 2/3 reference voltage is used as the non-inverting input for the first op amp, and the node with 1/3 reference voltage is used to compare on the inverting input of the second op amp. This will come into play later. The other pins on these comparators are connected to a capacitor. As this capacitor charges above 1/3 of the reference voltage, this capacitor's output will turn high, setting the pin of the SR latch, which I will talk about later. Additionally, it will continue to charge until it reaches 2/3 of the reference voltage, which will then make the output of this comparator high, resetting the SR latch, which I will talk about later. This circuit uses 2 NOR gates to create a set-reset latch, or an SR latch. An SR latch is a fundamental digital circuit that acts as a 1-bit memory, storing a state that can be set or reset using 2 inputs, S and R. The truth table for a NOR gate dictates that the output only is high when both inputs are low. Additionally, these 2 NOR gates are configured in a way that makes only one high at a time, hence Q and not Q, because the output of this NOR gate feeds into the input of this NOR gate. So if this is low and low, this will be high, so then this cannot be also high. So when the circuit is first turned on, this capacitor's voltage is near 0. The set part will be high because this is greater than this, setting the latch. As the capacitor continues to charge above 2/3 reference voltage, this will immediately trigger the reset pin, resetting the high output. This then feeds into a transistor that discharges the capacitor, restarting the whole process again, hence the oscillation of the circuit. The purpose of this NOT gate is to strengthen the output and restrict it to a strict 0 volts or 5 volts. This is why we take the output from not Q and then we NOT it again, making it Q. It wouldn't really matter either way because this not Q output will still oscillate at the same frequency of Q. They'll just be at different states at any given time. Now let's talk about the discharging that happens when the output goes high. So here we have the not Q output through a series resistor hitting the base pin of the NPN transistor, which leads to the capacitor discharging through here. It has a path to ground. Additionally, these values of R1, R2, and the capacitor dictate the frequency because the value of R2 dictates the length it takes to discharge, and the value of R1 plus R2 is the amount of time it takes to charge. Modifying these values will adjust the frequency of the output of the 555. Additionally, we can use the Arduino Nano to monitor the output of the 555. I have also attached a potentiometer in series to R2 to modify the frequency, which will show in real time in the graph displayed right now. As you can see, as I turn this capacitor, the time it takes for the capacitor to charge and discharge gets longer. This affects the time low and the time high of the digital output, modifying the frequency. Thank you for watching my video about the UNPACKED 555 timer. I hope you learned something today.